Okay, you are alive.
So hello everybody, my name is Bernhard Kodre. I'm one of the managing directors of Global Hydro Energy in Austria. Global Hydro is a very well-known manufacturer of hydropower plants and turbines. So we deliver turbines as well as the complete electrical and mechanical equipment for hydropower plants. So the company size is roughly 300 employees with 13 subsidiaries around the world, and the headquarters in Austria with a turnover of around about 60 million euros. I would like to show you an example and a showcase, especially in the field of the water supply and wastewater treatment in order to gain energy recovery and how to save energy costs by use of hydropower in your system. So if you start with the presentation, I would like to show you a very a common situation on the water supply. You see here a water supply dam, a water reservoir in Santa Catarina in Brazil. And as you can see, there is a big outflow of water. This is the echo flow for the river below the water reservoir. And this is at the moment unused. And what I would like to show you is some references and some examples how you could use this potential for energy recovery in order to optimize energy costs and to use this hydropower potential on your site and within your network. So what is the typical situation as far as I have seen in many examples around the world in water supply systems? So there are a lot of water reservoir dams that are not used for energy recovery. And as you might know, water supply companies suffer from big energy costs based on the big energy consumption of pumps and other consumers in the network as well as in the water treatment plants. And there is a big potential of saving energy costs by energy recovery for own use, for example, within your own network, or by connecting to the grid and getting some feed-in tariff in order to compensate energy costs. So the big benefit in that situation compared to a greenfield hydropower project is that the investment costs, especially regarding the civil costs, are rather low. The infrastructure normally is already in place, as you can see here in that example. The dam and everything is in place, and all you need is to use this existing infrastructure and to implement a turbine in order to gain the benefit from the potential that you have at this site. So civil construction costs would be rather low. Only the investment cost for the equipment would be applicable, and therefore the return on investment is rather quick. In some examples, already between 2 and 3 years. So if you compare that to a traditional greenfield hydropower project, where the return on investment is between 15 and 20 years, it is a rather attractive use case for the implementation of hydropower. Other possibilities to implement energy recovery would be, for example, at the intake of a water treatment plant, where you might have some significant inflow from a certain area into the water treatment plant and use this pressure and this water flow there in a hydropower turbine. Or another example, to replace pressure reduction valves in water distribution networks by the use of turbines at the outflow of wastewater treatment plants, for example, or even in the use of turbines in irrigation channels. All these would be some possibilities, and the use of a potential for energy recovery and for getting some power out of your own water supply network and water supply facilities. So how could we achieve these objectives? So hydropower is a very old technology, as you might know. It's a very traditional sector, but nevertheless, we could do some innovations in that field as well by developing a very compact hydropower turbine solution. This concept is called a Smart T. And we have this concept ready to use as a turbine within a container, fully operational. And that means that you don't need a big investment in civil construction costs. It's rather low in terms of space that you need, and it is fully installed and operational. So there would be a possibility to use on your site a power plant within a 20 feet standard container up to 1 megawatt. So if you implement this container, you have a reduction of the total costs. You don't need big investments on the powerhouse, and it is fully installed and already tested and pre-configured. So the site installation and the time to implement this concept is rather low compared to a normal turbine setup that we have. So the Francis turbine is typically an application that you can use in a middle pressure environment in a net head between let's say 15 and 50 meters or 80 meters maximum, and up to 1 megawatt could be gained out of such an application. The second possibility would be the Pelton, which is more for high-head applications, for example, in the inflow of the water treatment plant. If you have a net head, so this means a height difference of 80, 100 or 200 meters. It's the same concept. It would be delivered on a frame or in a container, where you have the pre-installed package unit, which is factory tested and ready to install on site with a very low effort. So what is the approach that we have on a Smart T turbine? So the concept in principle is that we would prefer to use standardized modules that we can put in place for the energy recovery, especially in the field of water treatment, water supply, and reservoirs, where we have a very good hydraulic design and a high efficiency, so that the output is rather optimized, that you get the best possible output to fit into the grid and to get the best tariff. To have an optimized size for low transport price, and a compact and assembled unit that you can lower the installation time. So it's more or less a standardized unit that is used for a certain parameter that you have in your network, like net head and flow, and then you can implement this turbine in order to gain the benefit of energy recovery in your network. So this would be a typical situation how you implement that kind of a turbine. So it is pretty easy to implement. So if you remember the picture of the water reservoir and the dam, the outflow that is unused at the moment. So that means you would install a platform, so to speak, where you can implement and install this turbine in order to connect to the outflow of the water reservoir or the dam, and then gain the benefit of the energy recovery by using the turbine, connecting to the next possible grid, and get the benefit of the feed-in tariff. So it's very easy to use. The concept would be in a way that we design the turbine based on your parameters, use the standardized components of the Smart T concept, manufacture, transport to site, and install within a few days, maximum 1.5 weeks, roughly, that you can be operational on your water reservoir and the dam. The only thing that you would need is a small civil construction for the platform, the basement, and a pipe connection to the outflow of the dam, and install this unit in a way that you can use it rather quickly. So the benefit of this system is that we have a rather standardized way to implement the Smart T units, but on the other side, it is rather limited in terms of the capacity. So the normal capacity range is from 100 kilowatt power output up to 1 megawatt, with different parameters like in the Francis turbine and the Pelton turbine with specific flow values. This has to be designed based on your specific situation and can be determined, of course, based on the data that are available, and would be designed and implemented accordingly. So just to show you a few examples how we would realize this kind of hydropower turbine and unit in certain references. I would like to show you a few examples. Very general here for the Smart T unit here in Iceland, where we, for example, have several units in place named Kalda and Tvera for 400 kilowatt Pelton. It was installed on a frame, delivered on a truck, very easily installed in a very small powerhouse. So this would be easily an application that could be used at the inflow, for example, of a water treatment plant, and used for energy recovery. We can also show the second type of turbine that we use here, which is a Francis turbine. The Francis turbine here delivered on a frame to a bigger power plant in Turkey, where we use this Smart T unit for energy recovery on the echo flow of the dam. And you can easily see here that it is transported just in one piece on the truck, installed within a few days in the powerhouse, connected to the penstock, and then connected to the grid in order to feed in power to the grid. So let me summarize before I come to very specific references for water supply and wastewater treatment. What are the possible applications of the Smart T concept of this turbine? So the very basic application is just a mini hydropower project where you have a site with a certain heat flow, and where you use this turbine to connect to the grid and gain the benefit of the feed-in tariff. It is also one of the main applications, the rural electrification, which means, for example, the replacement of diesel generators in remote areas, where with the use of hydropower, you would use these units to electrify, for example, remote areas or municipalities or small villages that are not connected to the grid and that would rely on a diesel generator. And hydropower is then a very good possibility to get a constant power supply, and as well as, of course, a reduction of emissions in CO2 by replacing the diesel generators. It would be a possibility to supply microgrids as well as hybrid power by the use in combination of hydropower, solar, and battery. Also possible is the application within microgrids for mines, factories, or resorts, and especially for irrigation channels, dams, drinking water supply systems, or wastewater treatment. So the combination between hydropower, solar panels, wind, and energy storage like battery or pump storage could lead to a concept of hybrid energy. So you could combine, if we again think of a water reservoir, you could think of using the outflow in a turbine with the Smart T unit. You could use floating solar cells on the water supply, combine both in one concept, also with energy storage, and then feed into the grid and get the benefit of the best tariff by the combination of hydropower, solar power, and battery storage. So you can optimize your feed-in tariff, for example, and feed in when the tariff is higher, and store in the battery when the tariff is lower, for example. So there are different possibilities to deal with the possibility of renewables in combination between hydropower, solar, wind, storage, and all of this in one concept to be used in your system of water supply and wastewater treatment. So in order to give you a better impression of what is possible and what we already realized, I can show you some references. So the first would be, there is implemented a small Pelton turbine supplied by Global Hydro in the wastewater treatment plant in Niederrhein, where we have a flow of 38 liters per second and a net head of 230 meters roughly. It's a very small application with 76 kilowatt, but nevertheless, with the constant production of 76 kilowatt, but just the inflow of the wastewater treatment plant after the core screen down to the wastewater treatment plant at the end of the hill, there is a constant energy recovery within the wastewater treatment plant, and therefore a permanent optimization of the energy costs and some benefits of the inflow of the wastewater treatment plant used by the hydropower system. Another very small application is implemented in the drinking water supply network in the city of Salzburg in Austria, like a 60 kilowatt turbine that is implemented directly into the distribution network of the drinking water supply. We also have a similar application in Tyrol with a very small flow and a high net head of 350 meter with 250 kilowatt. You see also in the type of the housing, everything is stainless steel. There is also a possibility, especially for the application of a turbine in the drinking water supply network, that the material quality is according the needs and the specification of the drinking water supply. And with 245 kilowatt peak power output, you can recover energy accordingly comparable to, let's say, a pump that you have in your network, and to compensate the energy consumption of that pump in another occasion in your network. There's another possibility here in Norway, where we implemented a small Pelton turbine within the drinking water supply with a range of 105 kilowatt. And you will see later on in the application here in Italy, which is rather big in terms of the flow and the head with 150 kilowatt. And one of the biggest that we realized is at the inflow of the drinking water treatment plant in Ramat in Iran, where we have a peak power output of almost 500 kilowatt, which is a pretty good power output that you can use within the water treatment plant. The same here. The biggest application that we have so far in Norway is 1.5 megawatt, also implemented within the drinking water supply in the town of Geração in Norway. So what I wanted to show you here in this short presentation is just to give you an impression what is possible in order to save energy costs in your system by the use of hydropower, where you could see that there is a certain potential available that could be used to optimize your costs, and that any investment that is done in that field is a payback time which is rather low compared to any other project in the hydropower field, because the infrastructure is already there, and investment costs are, compared to other projects, rather low. So the situation normally is in a way that the conditions are rather good to implement a hydropower station at your site and to use the potential that is lost day by day, because the water is just flowing through your system or running out of your system without being used by a hydropower system, especially by such a compact unit that we could provide here with the Smart T system. So I hope I could give you a good overview, and of course would be happy to answer any question that will be upcoming in the next minutes. Thanks a lot.